Greetings to all. This is Gurleen Kaur. I am currently pursuing my Masters in Construction Engineering and Management at CEPT University. As a part of our Studio 2, that is Construction Project Execution, Monitoring and Control, the execution phase of an ongoing construction project was studied. It is the successful implementation of all the planned activities to meet the project's objectives within the constraints of time, cost, and quality. The portfolio is a collection of selected deliverables done as a part of the course. Commencing with the project brief, the project selected for study is a corporate house building being constructed for a trading company in the SEZ zone in the gift city. The type of contract is item rate. The scope of work of the contractor is construction of 3 basements in ground plus 18 floors. It includes all the activities from excavation to finishing. The building has a height of 88.75 meters and is aiming to have IGBC Platinum rating. It is a greenfield project with total site area of 14,104 square meters, total built up area of 47,754 square meters, and estimated cost of construction of around 156 crores. Progressing to delve deeper into the content studied as a part of the studio, first up is the pour planning. It essentially involves organizing and coordinating all the necessary activities related to pouring concrete in a structure. In this section, formwork planning has been discussed in detail. There are a total of 6 pours in the basements and 3 pours in the typical floor layout, that is the tower area, the bifurcation of which is as depicted in the image. The study has been divided as per the types of formworks used. For the vertical elements, that is the columns, shear walls and the lift walls, peri-Henset alpha is being used. For horizontal elements, that is the slabs and the beams, there is the use of conventional 12 mm ply, and for scaffolding, couplock system is being used. The number of each component required was calculated as per the coefficients derived. For the derivation of the same, a fixed area on site was observed and respective grids were prepared. The components in the grids were counted as per the actual site observation. Slab and the beam plies have been calculated separately. For the slab, only the slab bottom plies were counted, and for beam, the beam bottoms and the beam verticals were counted separately. For the beam verticals, the outer and the inner end depths were considered, deducting the slab depth on the inner end. Similarly, for the couplock system, the components, that is the couplock verticals, ledgers, runners in the observed area were counted. Also, 100% back props were considered on the consecutive lower floor, which consists of the GIF props and the tripods. The table shows the typical pattern in which the elements of couplock system were calculated for each pour. The similar way has been done for the slab and the beam also. By counting for the given grids, the requirement for the entire pour was calculated by multiplying with the respective pour areas. The main considerations taken were: for calculating the slab horizontal plies, the area taken was total pour area minus the beam area, and also the beam depth was subtracted from the total floor height to calculate the height up to which the column formwork would be required. Calculation of column formwork has been done slightly different from that of the scaffolding and the horizontal elements. The figure shows the typical assembly of a column formwork along with its various components. The HSA panels are joined by tie rods and wing nuts horizontally as shown in the plan, and vertically by wedge clips one above the other. There are a total of 16 columns in the tower area which have been studied under 5 categories divided as per their sizes. Each category has use of different sized panels. The number of components have been arrived at by calculating each one's number going per panel and by multiplying quantity per column with the number of columns. The quantity per category has been calculated. For instance, given below in the table is one category having two columns C1 and C4. It has use of three sized panels, that is 1200 by 900, 1200 by 600 and 1200 by 450 mm panels. All the components per panel have been added as per site observations and the total number of components required have been derived. For making the set code repetition, the entire project's schedule was made in MSP. taking data from the previous pours that have been casted and predicting for the upper flows. The site has one full set for the tar area, which is being repeated one above the other flows, and the ply is being replaced after every 3 flows. The figure shows the repetition of sets on the consecutive floors vertically, denoted by color coding from B3 till the second floor roof slab, which would be followed similar way till the 18th floor. Coming to the direct cost of formwork, the material cost is calculated for all by multiplying the pour-wise quantities with the unit cost. The labor productivity similarly per pour has been used to calculate the labor cost. The TEP and the water electricity cost is considered 1% of the sum of the material and the labor cost. Considering the number of repetition differently for each material, the cost per repetition is then arrived at. Next up is the material and inventory management. Material management is the strategic planning of acquiring, storing, handling and distributing all the materials required on the site. The entire material management process is being done through the site store, the layout of which is as shown in the figure. Also, the material requisition process on site was studied. It starts with physical stock checking on site, after which the requisition request is raised from the site store on ERP. The raised request is approved by the project manager on site and sent to the head office. Quotations from the already approved 3 vendors are taken and sent for approval from the PMC, as it is the supreme decision taking authority in the project due to absence of all-time client representative. After approval, the purchase order is raised from the head office and material is supplied to the site. It is measured and custom clearance certificate from the gift SEZ along with the challan is submitted at the site. After passing all the quality checks, the goods receipt note is issued from the site store and the unloading of material is done. In the inventory management, the concept of EOQ has been learnt. It is the quantity of material that must be ordered to maintain the inventory at minimum cost. The EOQ model has been prepared for steel consumption, for which the actual consumption from the last 6 months was taken from site, and for the upcoming 6 months from the upcoming pours predicted as per the pour planning schedule. The purchase price was taken from the unit price rate as per the BOQ. Carrying cost was taken to be 5% of the purchase price, and the ordering price consists of the price required for the involvement of people and resources in the process. Altogether, 3 of them make up the annual inventory cost. From that, the EOQ, number of orders, and the optimal cycle time were calculated. This data was used for the preparation of classic EOQ model. From the classic model, as shown in the graph, it could be inferred that the ordering cost and the carrying cost curve intersect at a point that is 69.4 metric ton. This would be the economic order quantity, as both of them are inversely proportional. With increase in one, the other one is decreasing and vice versa. So at this point of intersection, the sum of both would be minimum, hence it would be the economic order quantity. Coming to the model with planned shortage, it was prepared by adding shortage period in the classic EOQ model prepared. It would denote the waiting time in case of material shortage. From the graph, it could be inferred the maximum inventory level after reordering would be 62.07 metric tons. For the first 16 days, the value of stocks is positive, and for the next 3 days, it comes out to be negative, which denotes the shortage period. So out of the total cycle time of 19 days, the maximum shortage observed would be of 10.4 metric tons. Further, in case of occurrence of shortage on site, the overall budgeted cost of the project would be affected. To combat that, safety stock should be provided, which is as calculated in the model showing reorder point and safety stock with probabilistic demand. As seen in the graph on the lower left corner, it is evident that the total cost is minimum at 11.46 metric tons safety stock limit, which is the optimal safety stock. Based on that, the reorder point and the lead time in days are calculated. The model has been prepared keeping the probability of demand constant. As per that, the reorder quantity depicted by the red dots in the graph is found out, which is 68.89 metric tons, giving lead time of 8 days. Further, the reorder point for the next 2 months are predicted as shown in the graph, which comes out to be in on 15th, 22nd, 29th days and so on. There was an introduction to the lean methods of construction as a part of the studio. Lean methodology has three core concepts, that is maximizing value and enhancing productivity by elimination of waste in the process. As a part of that, a deliverable on value stream mapping was performed, in which the activity of erection of formwork panels in the lift well was observed for an entire day from 9:30 am to 8:15 pm. The area observed was 23.76 square meters, and a total of three, that is, two carpenters and one helper, were involved in the process. The formwork was erected in two layers up to a total height of 2.4 meters using 1200 mm high HSA panels. Till the end of the day, 26 panels were fixed. To perform the activity of VSM, the entire day's process was observed and made in MSP, and the time taken for each activity was noted down. The flow of activities started with the inspection of binded reinforcement bars, followed by erection of working platform, mobilization of tools, equipments and materials, and finally to the erection of panels. To prepare the current state time estimates, the observed time was categorized into value adding and non-value adding time. Non-value adding time is further of two types, that is non-value adding and non-value adding but necessary. As per the lean classification of waste categorization, that is downtime, each sub-activity was assigned a category, a few examples of which are given in the waste categorization table. As they are non-value adding, the duration of type 1 waste could be decreased and that of type 2 could be completely eliminated. Coming to the takt time calculations, it is the measure of the productivity. Current takt time has been calculated from the observation, that is the ratio of the time taken to the area observed. The targeted takt time is the ratio of the total time available for completing the activity to the total area that has to be covered. And the difference of both gives the total reduction in the time required. The duration of all the waste categories identified was brought down by application of various tools, namely 5S, PDCA, Kaizen, Just-in-Time, 5Eyes, etc. The main purpose is to cut down all the non-value adding activities and streamline the process. In the future state map, the cycle time of each activity is reduced, decreasing the overall lead time of the process. The main delay observed was on mobilization of panels and in getting approvals for the commencement of work, which could be done a day prior to make the process faster. Given below is the future state mapping showing the application of lean tools on the current state activity durations. Comparing current with the future state, it could be observed that the non-value adding time was reduced from 450 to 253 minutes, reducing the overall cycle time by 196 minutes. Also, the achieved takt time was 18.45 minutes per square meter, which is near to the targeted takt time, that is 19.54 minutes per square meter. Moving further with the quality management, it is a crucial part of any project that involves implementation of all the processes to ensure the execution is being carried out as per the specified standards of quality. As the site is in the GIFT City area, so it was important to study the GIFT City's QA/QC framework that ensures quality provision by conducting regular QC meetings, on-site inspections, and off-site quality control by collecting all the material test reports, samples, certificates, and by maintaining all the documents. The contractor's quality management plan on-site consists of quality assurance plan that gives the list of tests required for all the incoming materials, and the field quality plan that gives the characteristics of all the procedures executed on the site. Given on the right is an example of the reinforcement quality checking that includes physical, chemical and visual tests. It is performed by the contractor in the presence of PMC's representative or sometimes client's representative as a random witness. The QC lab for the site is located near the batching plant, which is as shown in the layout. The QC lab, curing tank and the storeroom for document storage of the QC lab was studied as a part of the deliverable. The layout of the batching plant shows them marked in red. Also, there are 4 curing tanks present of 1.8 meter by 0.9 meter. They are used for cube tests at 7 days, 28 days and 56 days respectively. Various equipments that are required in the QC lab and also the tests that are required to be carried out for each material were studied. The layout of the existing QC lab was prepared to show the arrangement of the lab. The list of equipments present in the lab are marked in the layout. Comparing the existing layout with the standard CPWD and NABL guidelines, a new arrangement was proposed. The existing lab has opening near the ceiling for ventilation, which is otherwise not good for lab equipments as moisture might affect them. Also, there is lack of covered storage space and organization in the lab. In the proposed arrangement, there is addition of storage racks, covered storage space below the shelf for storage of delicate equipments and also of fire safety equipments, which is very important part of any lab. The proposed arrangement is as shown in the view. Summing it up all, in our pore planning analysis, we extensively explored various formwork strategies, understood various formwork types, and calculated elements via the coefficient method. Additionally, through the Microsoft project scheduling, we gained insights into optimizing formwork repetition and movement, both horizontally and vertically. Through the study of material management, the material requisition process and the on-site material usage process has been understood. Utilizing EOQ models, we have developed our skills in minimizing inventory costs while ensuring optimal stock levels based on the annual consumption. As an integral part of introducing lean construction methods, our exploration included the practical exercise of value stream mapping. Through this, we gained valuable insights into the flow of activities within our construction processes, while also identifying various types of wastes that affect the efficiency. Furthermore, this exercise empowered us with the knowledge and tools necessary to streamline our operations by eliminating the delays through the application of lean principles. Analyzing the on-site quality control lab against the CPWD standards unveiled equipment requirements, calibration schedules, and the material testing protocols. Proposing changes based on the identified gaps has optimized the QC lab arrangement. This studio emphasized hands-on learning by providing exposure to real construction sites. Through discussions, observations, and analysis, both the efficiencies as well as the inefficiencies were identified, and by proposing improvements in the process, a forward-thinking mindset based on continuous improvement has been developed. Thank you.